Hello students, welcome to EPG Pathshala. I am Dr. Kapindra from Kirodimal College, University of Delhi. Today we will discuss about module life table, survivorship curve and fecundity table. For a population, the surviving individuals are more significant for a population than the dead ones. The death rate can be represented by survivorship curves or life tables, both of which provide an estimate of organisms surviving at various ages. The data from a cohort life table is usually shown as survivorship curve for a particular population, and it depicts age specific mortality through survivorship. Life tables and survivorship curve are based on data obtained from one population of the species at a particular time and under certain environmental conditions. In the previous module, we studied about concept and construction of life table, and in this module we shall understand survivorship curve and also learn about fecundity table. Survivorship curve we can represent the life table on a semi-logarithmic paper, where the number of individuals surviving is plotted on vertical axis on a logarithmic scale, and time or age class is on the horizontal axis on the arithmetic scale called survivorship curve. Survivorship curve can be classified into three types, which act as standard against which real life survivorship curve of different organisms can be compared. It represents the different nature of survivors in different types of populations. A. Highly convex curve. This type of curve is also called as type 1 curve. It is the characteristic of those species in which the mortality rate of the population is low up to the end of the lifespan. The organism live throughout its age, and thus such species survive throughout their lifespan with low mortality rate in young and adult individuals. Many species of large animals such as deer, mountain sheep, man and small rotifers show such type of curves. Among various large sized perennial plants, generally they die after reaching reproductive phase within a period of old age. Populations characterized by this type of survivorship generally have low birth rate. This is due to the fact that most young survive to reproduce, and their high birth rate would lead to runaway population growth. Type 2 or diagonal curve. This type of curve indicates an age specific constant survivorship. That means a constant rate of mortality occurs at every age group. Such a curve is characteristic of some animals such as hydra, gull, American robin, adult birds, rodents and reptiles as well as many perennial plants etc. exhibit type 2 curve. Type 3 is known as highly concave curve. This type of curve is the characteristic of those species in which mortality rate is high during the early life stages. Some birds, oysters, shellfish, many insects, oak tree and fishes exhibit this type of survivorship curve. In oysters, higher mortality occurs due to adverse environmental condition and predation in the early stages. In holometabolous insects, a stair type of survivorship curve is obtained as survival differ greatly in different stages of life history. In many birds, rabbit and mice, a slightly concave or sigmoid curve is formed. Higher mortality in the young one, however, mortality is low at adult stages. Populations characterized by a type 3 survivorship curve often needs to have high birth rates in order for the population size to remain constant. High birth rates ensure that enough young survive to reproduce age to the reproductive stage, thereby ensuring that the population continues to maintain itself. The shape of the survivorship curve can be used to pinpoint the critical period in the life of the organism. Wherever the curve becomes steeper, there is an increase in mortality indicating some environmental or developmental effects on the population. Salmon produces thousands of eggs, but only few of them survive and able to reach up to adult stage. If one egg in 10,000 survivors to become adult, it means that only 0.01% of the total energy invested is represented in the next generation of fish. Majority of the animals reproduce this way only. Most large animals are heteroparous, that means they live to reproduce repeatedly, but many species of insects and microorganisms are semiparous, that means they live and they reproduce only once and after that they die. The reproductive efforts of a semiparous species represent the ultimate expenditure of energy in order to produce as many eggs as possible. The given figure represents the survivorship curve of the song sparrow Melospiza melodia. The curve is typical of birds. These three types of generalized survivorship curves can be used to compare the survival of a species. In fact, no population in the real world has a constant age specific survival rate throughout the whole life span. Many survivorship curves show components of these three generalized types at different times in the life history of a species. In song sparrow Melospiza, Melodia, there is high mortality in juvenile stage, that is type 3 survivorship curve, and in adult stage it becomes linear, which represent type 2 or diagonal type survivorship curve. Mortality curve. When mortality rate, that is Qx, of the life table is plotted against age, that is x, it is called as mortality curve. Mortality curve has two phases. The first phase is juvenile phase, where mortality rate is high, and second phase is post juvenile phase, in which mortality rate first decreases with increase in age, and then mortality rate that start increasing with age after a period of low mortality. Usually the mortality curve is J shape, and such curve indicates the rate of mortality throughout the slope of line is more as compared to survivorship curve. Mortality curve for the life tables presented in the figure of grey squirrel. For the grey squirrel cohort, the curve consists of two parts: a juvenile phase in which the rate of mortality is high, and a post juvenile phase in which the rate decreases with age until mortality reaches some low points, after which it increases again. Fecundity table. A fecundity table demonstrates the mortality schedule of a population. The next step in the life table is to combine the mortality and reproduction to estimate the net population change. Alfred Lochta in 1925 derived one demographic parameter called intrinsic capacity of increase. Any population in the nature has its mean longevity, growth, mortality and speed of development. These parameters are not constant for any species. Their mean value is determined by environment and innate quality of the organism. Due to fluctuation in environment such as winter and summer, the population cannot grow continuously. The population increases in favorable condition and the population decreases if the condition become unfavorable. The organisms have great intrinsic capacity of increase. However, in nature there is always a balance in the population size. For example, female Helicoverpa armigera, it is a polyphagous pest which can produce 1200 to 1600 eggs in its lifetime. Even then, there is a balance in the population size of this pest due to environment and different biological agents. Therefore, in nature there is actual rate of change of population occurs in response to the environment, age structure and genetic composition. A standard convention in the study of population is to express birth rates as birth per 1000 population per unit time. This is calculated by dividing the number of births over a given time period by the population size at the beginning and multiplying by 1000. This will represent the crude birth rate, and this can be further improved by taking two most important factors. First, in sexually reproducing population, only females can give birth to young ones, and second, the number of births given by female varies with age. Hence, birth rate can be expressed as the number of births per female of age x. As the size of population is increased due to reproduction by females, the age specific birth rate can be further modified by determining mean number of females born to a female in each age group, that is Bx. Following given data for age specific birth rates of grey squirrel population can be used to construct fecundity life table. At the beginning, at age 0, females did not produce any offsprings, so the value of Bx is 0. At this age 1, female produces an average of 2 female offsprings, females of age 2 and 3. The average number of female offsprings produced, that is Bx, increases to 3, and after that this Bx declines to 2 when females reaches to age 4. By the age of 5, females cannot produce offsprings, therefore, the value of Bx is again reaches to 0. The summation of Bx value of all age group provides an estimate of the average number of female offsprings produced by female in her lifetime. It is called as gross reproductive rate. In the above example, the gross reproductive rate of grey squirrel population is 10. However, in this example, value assumes that the maximum survival of the female squirrel is 5 years. Now, next step is to measure net reproductive rate that integrate the age specific birth rate and the probability of survival of female to any specific age. After knowing the fertility schedule, we call it as Bx, and proportion surviving, that is small lx. Another important parameter, that is net reproductive rate, which is denoted by R naught, can be calculated. Net reproductive rate, that is calculated by the formula number of female offsprings produced in generation t plus 1 divided by number of female offspring produced in generation t. Net reproductive rate is thus the multiplication rate per generation, and it can be calculated by multiplying Lx and Bx schedules and summing over all age group. If net reproductive rate is equal to 1, the population is replacing itself, and if the rate is below the value of 1, then the population will not replace itself. The age specific birth rate of grey squirrel population can be used for constructing a fecundity or fertility table. The fecundity table uses the survivorship column, that is Lx, and age specific birth rate, that is Bx, from the life table data. In the fecundity table, initially Bx increases with the age, whereas proportion survivorship, that is Lx, declines with each age group. To adjust for mortality, each Bx value is multiplied by its corresponding proportion survival, that is Lx values. The resulting value Lx Bx gives the average number of female offsprings produced in each age class, adjusted for survivorship. Therefore, the value of Bx for 1 year old female is 2, but when it is adjusted for survival, the value declines to 0.6. Similarly, for female of age group 2, the value of Bx is 3 and Lx Bx value declines to 0.45. It represents that the survival of adult female is poor. The value of Lx Bx are summed over all ages at which reproduction occurs, that will give net reproductive rate, which is calculated by formula summation of Lx Bx, and the value that we will get is 1.4. Therefore, the net reproductive rate of grey squirrel population is 1.4. If value of R naught is greater than 1, females are more than replacing themselves. If in this example R naught value of grey squirrel suggests a growing population of females, the difference between gross reproductive rate and net reproductive rate, that is 10 and 1.4 respectively, reflects that only a small proportion of female grey squirrel will survive to the maximum age and produce 10 female offsprings. Because the value of R naught is a function of the age specific pattern of the birth and survivorship, it is a product of the life history characteristic. The allocation to the reproduction, the timing of reproduction, the trade off between the size and number of offspring produced, and the degree of parental care. The net reproductive rate therefore provides a means of evaluating both the individual fitness and population consequences of specific life history characteristics. The fecundity table of the human female in the United States is presented in the given table. If human population of the United States continue to grow at these rates, it would multiply 1.039 times in each generation. The table represents fecundity table for women in United States. In the natural condition, environment is always fluctuating, sometimes favorable and sometimes the environment become unfavorable for the organisms. When environmental conditions are favorable, there is increase in population size, and if conditions are adverse, population number start declining. Therefore, in the natural state, a population shows the actual change that can vary from positive to negative due to change in social structure, age distribution, genetic composition or change in environmental factors. An organism innate capacity of increase, we also call it as a Malthusian parameter. It depends on its fertility, longevity and development speed. These processes are integrated with natality rate and mortality rate. The natality rate can be explained by birth schedule, egg or seed production of the population, the number of female offsprings produced by per female aged x to x plus 1 is considered as fertility schedule, that is Bx. Usually females are counted for fertility schedule and demographers consider only females as a population which further produces more females. The following given hypothetical data can be used to illustrate how the intrinsic capacity of increase, that is small r, can be calculated from biological data. The value of Lx and Bx from the table are sufficient to allow calculation of intrinsic capacity of increase in number, which is denoted by small r. First step is to calculate the net reproductive rate, that is capital R naught, which is already explained above in this module. For the given data, net reproductive rate is 3, which clearly indicate that the population can triple its size in each generation. But how long is a generation? The length of a generation, that is capital G, can be explained as the mean period between the birth of parents and the production of the offsprings. Dublin and Lotka in 1925 defined the mean length of a generation by the formula, that is capital G, that is equal to summation of Lx, Bx and x divided by summation of Lx, Bx, which is further derived, that is capital summation of Lx, Bx into x divided by capital R naught. For the given hypothetical data, the value of G is 1.3 years. Knowing the value of capital R naught and capital G, we can calculate intrinsic capacity of increase, that is small r, by applying the formula. So, now we get log E in bracket 3 divided by 1.3, and now we will get the value of 0.82 per individual per year. Now, students, let us summarize what we have studied in this module. A population is a localized group of individuals belonging to the same species. The surviving individuals are more significant for a population than the dead. The death rate can be represented by survivorship curve. Survivorship curve can be classified into 3 types. It represents different nature of survivors in different types of populations. Type 1 curve is the characteristic of the species in which the mortality rate of the population is low up to the end of the lifespan or up to the old age. Type 2 curve or diagonal curve indicates an age specific constant rate of mortality. Type 3 curve or concave curve is the characteristics of those species in which mortality rate is high during the early life stages. These 3 types of generalized survivorship curve can be used to compare the survival of a species. When mortality rate of the life table is plotted against age, it is called as mortality curve. It has 2 phases, that is juvenile phase and post juvenile phase. Any population in the nature has its mean longevity, growth, mortality and speed of development. Due to fluctuation in the environment such as winter and summer, the population cannot grow continuously. A standard convention in the study of population is to express birth rates as birth per 1000 population per unit time. As the size of population is increased due to reproduction by females, the age specific birth rate can be further modified by determining mean number of females born to a female in each age group. After knowing the fertility schedule Bx and proportion surviving Lx, another important parameter, that is net reproductive rate capital R naught, can be calculated. Net reproductive rate is thus the multiplication rate per generation. The net reproductive rate provides a mean of evaluating both the individual fitness and population consequences of specific life history characteristics. An organism innate capacity of increase depends on its fertility, longevity and development speed. These processes are integrated with natality rate and mortality rate. The length of a generation capital G can be explained as the mean period between the birth of parents and the production of the offsprings. Thank you.